Yo, what's up? It's your boy Mr. AC, and what I got for you guys today is going over primarily, and we are on year number, so let's go ahead and get started. Moving on to question number 2004. Question number 6. Now, if you notice, we haven't done some of these in a while, and they're slowly now starting to creep up, which is our slope fields. Now, our slope fields, as you know, there's two things we need to do. So if you notice, on the axis provided, sketch a slope field for the given differential equation at the 12 points indicated. What are the 12 points indicated? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's basically all these 12 right here. I know this one is hard to see at 0, but there is one there. So how do we do our slope fields more efficiently? Well, the best way to do it is to find when does the slopes have a slope of 0, and then after that we can kind of go in strategically. Well, if I look at this equation, if I plug in a y value of 1, 1 minus 1 is 0, 0 times anything is 0. So when my y value is 1, I'm going to have a slope of 0. So I know right here is a slope of 0, a slope of 0 here, and a slope of 0 here. Now, what's the good news? Well, I know x squared is going to be positive no matter what. But if I plug in 0 for x, what's going to happen? Well, 0 squared is 0. 0 times anything is 0. So I also need to put those slope fields as well. Well, where is x equal to 0? Well, x is going to be equal to 0 right here at this point. That is when x is obviously 0. And then we can fill in any rest of these right here, which, look at this. Well, x value is 0 here too. The x value is 0 here too. We get a lot of slopes of 0 right here. This is when y equals 1. This is when x equals 0, because we didn't change our x value, and no matter what the y value is, it'll be 0 because it's multiplied with 0. Hopefully that makes sense. So now we can kind of get rid of these 6 points really strategically. So notice how finding the 0 slopes is going to be really helpful. Now let's go ahead and find the rest of the slopes. So I prefer to do these ones right here, just kind of go at it in a strategic way. If I plug in, this is again 1 comma 0, right? So if I plug in 1 comma 0, I get 1 squared, which is 1. 0 minus 1 is negative 1, so we get a slope of negative 1. I'm going to plug in negative 1 into this function now. Negative 1 squared is 1, and then this is 0 minus 1, negative 1, so this is a slope of negative 1. So notice how in this problem, going sideways to me just seemed the most effective because the y value doesn't change. So let's go up here now. This is 1 comma 2. We plug in the 1 for the x. 1 squared is 1. 2 minus 1 is 1. So this is a positive 1. If I go over here, negative 1 squared is positive. 2 minus 1 is 1, and we get a slope of positive 1. All right, now I'm going to go to this next point, 1 comma 3. This is, again, 1 squared is 1, 3 is 2, so the slope was going to be a little, oh my god, the slope is going to be a little bit steeper, and then it's going to be the same thing over here, and this is going to be a little bit steeper there. So that is part A, getting our slope fields drawn. So we took care of that. Now let's go ahead and go to part B. It says, while the slope field in part A is drawn at 12 points, it is defined at every point in the x and y plane. Describe all the points in the xy plane for which the slopes are positive. We want to have positive slopes. Now, what do we know so far about our function? Well, we know x squared will always be positive, right? And we know then if this is always positive, really if we want our slopes to be positive, we need this to be positive. Well, how do we make this work? Well, first thing we need to do for part B is we're going to say for part B, we're going to say all the points in the xy plane for which the slopes are positive are, so I obviously, just for the sake of time, I'm not going to rewrite all this out, but we're going to literally write that down here and say are when, well, first things first, okay? If you notice here, x cannot equal 0. That's importance number 1. X cannot equal 0 because at 0 it is a slope of 0, right? So we need to say where it cannot be equal to. X cannot equal 0. We could also say and when y cannot equal 1, but then that's not going to work because I want you to notice that there is points down underneath here that are negative. So we need to know when is this positive, like I told you. Well, this is going to be positive if I write an inequality, right? We want this to be greater than 0, so we're going to solve this out, and this is only going to happen when y is greater than 1. Why does that make sense? Well, if I plug in 1, I get a slope of 0. So I'm not going to put the equal to symbol, right? That wouldn't make sense because then I'm going to include 0 slopes. I need it to be greater than 1. So we're going to say, describe all the points in the xy planes for which the slopes are positive. We're going to say all the points in the xy plane for which the slopes are positive are when x cannot equal 0 and y is greater than 1. And that's going to solve this problem because we are essentially excluding the 0 slopes and we're saying when y is greater than 1. So we know everything else, all the points, infinite points in the xy planes that are positive are when these two conditions are met. So hopefully that makes sense. That's going to take care of A and B. Let's go ahead and hop on to part C. Okay, so now we're going to go to part C. Find the particular solution, y equals f of x, to the differential equations with initial condition f of 0 equals 3. Again, the big hint here is y equals f of x. Find y equals f of x. They gave us a derivative. They want the original. The variables are not separated. We need to do the antiderivative and we need to separate the variables. So let's go ahead and do that. Well, what do we do with our first step? Our first step, probably by now is getting a little repetitive, but that's good. We're going to multiply dx to both sides. That way the dx's are on the same sides. These cancel. And then we're going to divide by y minus 1. So I'm going to put it over here. Y minus 1. Once we multiply dx to both sides, we divide by y minus 1. Again, we put a 1 as a placeholder on the top. Divided by y minus 1 dy is equal to x squared dx. And now that we have separated the variables correctly, we can now officially go ahead and do our antiderivative correctly. So we're going to take the antiderivative of this function. Now, this is a great one to do because this is 1 divided by y minus 1. This y minus 1 that's on the denominator does not have a power. You can essentially put parentheses if you want to. Now, this is a huge indicator that we're going to have to use our ln function. So the antiderivative of this is going to be ln absolute value of y minus 1. Don't forget, I'm going to make a big note of this because sometimes we take this for granted. We still need to take the derivative of the inside. What's the derivative of y minus 1? It's 1. So we're going to divide by 1, but we don't need to put it because it's 1. If it was any other number, we would. So then we're going to get equal to, and this is going to be x to the third divided by 3 plus c. Okay, let's go ahead and put 0 in for the x value, and let's go ahead and put 3 for the y value. So the 0 is going to go into the x, which is really nice because if I put the 0 into here, 0 to the third power is 0, everything cancels out, and we're going to get 0. So this is c, and let's plug in the 3. We're going to get ln absolute value of 3 minus 1. This is ln absolute value of 2, which is equal to c. What's the absolute value of 2? Well, that's just going to be ln of 2. There it is. Let's go ahead now and plug it back into my original right here. So we're going to get ln y minus 1. So we're going to get ln absolute value of y minus 1 is equal to x to the third divided by 3 plus ln of 2. So now we need to solve this out. We figured out our c value. We need to basically get y by itself. Well, how do we do that? Well, what's the opposite or the inverse operation of ln? Well, that's going to be e. So we're going to do e to the power of this, e to the power of this. And I'm going to go ahead and put a set of parentheses. Yeah, I could rewrite this. The e and the ln could cancel out to this side, but you know what? We don't need to do that. We don't. We just go ahead and solve this out, y'all. So let's do that. The e and the ln cancel. We're going to get y minus 1 is equal to e to the. There it is. It's going to look something like this. And really, really important, if you notice, I put an extra set of parentheses on the power of e so that they know that that was on the power of e and not like plus ln of 2 on the outside. Nonetheless, we need to solve this out. And now we can just add 1 to both sides. But bam, this is going to be gone. We get y is equal to e to the power of x to the third over 3 plus ln of 2 plus 1, and there is my function solved out with the initial condition all put in and everything. Hopefully y'all enjoyed. I'm out. Take care. Capiche?